In this chapter, we'll study about temperature and heat and how they're related. So temperature measures how hot an object is. Okay, it measures the average internal random kinetic energy per particle of the system. So it measures. So let me show you an app. Um, all right. So here, let's do this. Here we go. So we will fill this chamber with some gas. Okay, and the temperature of this gas is 300 degree Kelvin. That's roughly room temperature. That's on the Kelvin scale. We'll talk about that. The pressure is 20 atmosphere. And what temperature measures is the average speed. It measures the average kinetic energy of these particles. Okay, and so if, for instance, if I warm this gas up, and you can see that the temperature rose as I'm warming the gas up, you're speeding up the particles. Okay, so higher the temperature, higher the average kinetic energy per particle, and that's what temperature measures. Okay, so temperature is a measure of the average internal random kinetic energy per particle of the system. Okay, the temperature is a unique number that determines whether thermal energy will flow into or out of the substance. So if you have two objects, and if this is at 100 degrees Celsius and this is at 60 degrees Celsius, since this is at a higher temperature, heat will flow from here to there. Okay, so temperature determines whether heat will flow into the substance or out of the substance. Okay, now here's an interesting number. When the universe began 13.8 billion years ago, when the Big Bang happened, the temperature of the universe was 10 to the power of 39 Kelvin. Okay. All right, what this picture is showing you is, let's say this is a table. This end of the table is hotter than this end. What hotter means is these atoms are vibrating with greater amplitude, and they have greater energy than these guys. And as heat flows from here to there, when the temperature is all even, they'll all vibrate with the same amplitude, and their average energy will be the same. Okay, that's what equilibrium means. Okay. All right. When two objects are in thermal contact, they can exchange heat. Okay. Two objects in thermal contact with each other. When two objects are in thermal contact with each other, energy can be exchanged between them. Okay. So there are three ways of exchanging heat: via conduction, convection, or radiation, and we'll learn about these. And this will be important because we'll see how the body cools itself down when it overheats. Thermal equilibrium means when two objects have the same temperature, they are exchanging heat, but there's no net exchange of heat. If this guy gives up 10 joules of heat, he receives back 10 joules of heat. And then they are in thermal equilibrium. And when two objects are in thermal equilibrium, they have the same temperature. Okay, so 10 degrees Celsius, their temperature will be the same when they're in thermal equilibrium. So let's say 50 degrees Celsius, 50 degrees Celsius. So two bodies in thermal equilibrium have the same temperature. Now, interestingly enough, so let's say here's a metal object that's at 10 degrees Celsius, and here's a piece of wood that's at 10 degrees Celsius. Now, if you touch this will feel colder than this guy. Okay, so this is wood and this is steel, let's say. So why does this feel colder even though they're the same temperature? It turns out that steel is a good conductor of heat. So when you touch this, heat is conducted away from your body faster than when you touch the piece of wood. And humans, we are sensitive to rate of loss of heat rather than temperature. Okay, so for instance, here's a good one. Here, humans are to a large degree sensitive to energy fluxes, flow of heat rather than temperatures, which you can verify for yourself on a cold, dark morning in the outhouse of a mountain cabin equipped with wooden and metal toilet seats. Both seats are at the same temperature, but your backside, which is not a very good thermometer, is nevertheless very effective at telling you which is which. So again, the rate of heat loss is what we're more sensitive to. So, all right, now that we have defined temperature, which is a measure of the average kinetic energy per particle of the system, okay, let's talk about the scales that we use to measure temperatures. Okay, so there are three commonly used scales to measure temperature: the Celsius scale, Fahrenheit, and the Kelvin scale. Okay, to build any temperature scale, what you need is two physical phenomena that happen at the same temperature. Okay, so meaning no matter what time of the year you do, you find that ice will always melt at the same temperature, uh, assuming assuming at 1 atmosphere. Okay, so and in 1 atmosphere you find that water always boils at the same temperature. Okay, so you have these two physical phenomena, and the Celsius scale calls the melting point of ice as 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. The Fahrenheit guys call the melting point of ice, the melting point of water, as 32 degree Fahrenheit and 212 degrees Fahrenheit for boiling point. The Kelvin scale is 273 degree Kelvin and 373 degree Kelvin. Okay, and you can see that between the melting point of water and boiling point of water, there's 100 degree Kelvin and there's 100 degree Celsius. So it seems like these two temperature scales are the same, except their zeros are different. And so we'll come to why this was invented. You can see that this scale has 180 degrees between the same two temperatures. And so the Fahrenheit scale is a more finer scale. It's a finer grain scale. And so this is useful for humans. Okay. What these formulas give us how to convert between Celsius scale and Fahrenheit scale. So if you have the temperature on the Celsius scale, how do you convert it to Fahrenheit? Okay. And this formula gives you, when you have the temperature on the Celsius scale, how do you convert to Kelvin? So 20 degrees Celsius is 20 plus 273, 293 degree Kelvin. If you have 20 degrees Celsius is 20 divided by 5 is 4, 9 times 4 is 36, 36 plus 2, 68. So 20 degrees Celsius is equal to 68 degrees Fahrenheit. Okay, so anyway, these two formula allow you to convert from one scale to another. Okay, so now let's define absolute zero. Okay, so you saw in this app that temperature is a measure of the average kinetic energy. Okay, now let's cool it down. Let's cool the gas down. Now you can see that as you cool the gas down, the temperature decreased and these molecules slow down. Okay, what is the best you can do? The best you can do is stop all the molecules, and then you can't cool the material anymore. And when all the molecules cease, that's the lowest temperature possible, and that is absolute zero. Okay, so that's why this Kelvin scale was invented. Okay, the the coldest possible temperature on the Celsius scale is minus 273 degrees Celsius, and so this was called 0 degree Kelvin. Okay, that's an odd number for it to be the lowest temperature. So the Kelvin scale was invented just by adjusting the zero for the Celsius scale. Uh, so so absolute zero is the lowest possible temperature, and that's 0 degree Kelvin. Okay. So at absolute zero, all molecular motion ceases and internal energy of the system is zero. Here are some temperatures we measured. Okay, so at the center of a hydrogen bomb explosion, the temperature is 100 million degree Kelvin. The solar corona is 1,000,000 degree Kelvin. The surface of the sun, the temperature is about 6,000 Kelvin. Okay. So how do we measure this temperature? The temperature at the center of the explosion of a hydrogen bomb. Okay, all these remote temperatures, okay, are measured as follows. Okay, so for instance, the surface of the sun at the center of a hydrogen bomb explosion, and so on. All right, here's how they are measured. So let's go to this other app. Okay. Okay, when you have solids and liquids, okay, and dense gases, and when they're at they're heated, well, actually everything emits electromagnetic radiation. And what this is graph is telling you is the intensity of the radiation and versus the wavelength. The wavelength corresponds to the colors. You see different wavelengths have different colors of invisible light. Different wavelengths have different colors. Okay, so this is the intensity emitted by an object versus the wavelength. Okay, now you see, if you change the temperature, so again here what I'm doing is I'm changing the temperature of the object. Okay, as you change the temperature of the object, this curve changes. So the curve is unique for a given temperature. So to measure the temperature of an object, so for instance, if you wanted to measure this surface temperature of the sun, the surface temperature of the sun is roughly 5,900 Kelvin. All you have to do is measure the intensity for this color, intensity for this color, this color, this color. So for 4 or 5 different colors, you measure the intensity and find the curve that best fits it, and then you have the temperature. Okay, so that's how temperatures of all remote objects are measured. And in fact, the thermometers that the scanning thermometer we use to measure the temperature of a human being is also based on this idea. Okay. All right. All right, so here's the model. Here's the model for a solid. So here's a solid object, and when you heat it, its length increases, or it expands. Okay, so here is the model of a solid. Here are atoms at fixed locations, and when you heat the solid expands, meaning the forces between this atoms is modeled as springs, and the springs expand. The kinetic energy increases and their potential energy increases. So every atom moves further apart, and so the length of the object increases. This formula gives you the increase in length. The increase in length is proportional to the original length times the increase in temperature times a number that's dependent on the material. Alpha is the coefficient of linear expansion. Okay, and here are the coefficients of linear expansion for various material. Okay, so for iron, steel, this is 12 times 10 to the minus 6. So for instance, the change in length, if you had 1 meter of steel and you raise its temperature by 1 degree Celsius, alpha is 12 times 10 to the minus 6. Okay, so the length increase would be so 1 times 1 times 12, so that would be 0.012 into 10 to the minus 3 meters, and that is a millimeter, so 0.012 millimeter. Okay, so a 1 meter length of steel rod if you raise its temperature by 1 degree Celsius, its length will increase by 0.01 millimeter. So you ask, and that's a tiny amount, so you ask, why do we worry about that? Well, you'll see that this is important in many applications. Okay? And so that's why we're studying it. Okay, so for instance, here's a bridge in Michigan, and the center span is just under a mile long. And between the dead of the winter and the heat of the summer, it sees a temperature change of 100 degrees Celsius. Okay, and the center span over a year's time will expand 1.5 meters. That's the height of a person. Okay, so it would expand by the height of a person, and if you don't account for that, the bridge would collapse. So that's why in between spans they leave these expansion gaps, and you see this is how far the spans are separated in the winter, and in the summer they've closed. Okay, so if you didn't provide for that, these spans would push against each other and crumble. Yeah, so here's some train tracks where there were not enough expansion gaps, and they deformed, and so now a train can't go on that. This has to be fixed. Yeah. So heat is what flows from a hotter object to a colder object. Okay. So when you bring a hotter object in contact with a colder object, heat will flow from it. Okay. Now you saw that at any given temperature, these molecules vibrate, and the length depends on the temperature. So there's potential energy and kinetic energy. Okay. And when the object is hotter, some of this energy is transferred to a colder object. Okay. And heat is that energy. So heat is the internal energy transferred between objects because of temperature differences. So as heat flows from here to there, these guys vibrate with smaller frequencies, smaller amplitudes. Their kinetic energy decreases, they contract, the potential energy decreases, and stuff like that. So internal energy or thermal energy of the system is the random internal kinetic and potential energies of the atoms, okay, or of the microscopic constituents. So heat is so going back to, so for a gas, it's a simpler thing. So here we go. All right, actually so here are gas molecules, and internal energy is this random kinetic energy of the particle. And when heat flows, this energy of the gas particle reduces, and so internal energy is the heat energy. So units of heat, calorie is a unit of heat, and in the SI unit, joules are the unit of energy. Remember, heat is a form of energy. And 1 calorie is the heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, so that's how you define a calorie. And a kilocalorie, 1,000 calories, is 1 food calorie. Okay, so this calorie is written with a small c, the food calorie is written with a big C. So, well, but in this course, we'll always write a kilocalories. So a kilocalorie is 1,000 calories. And again, 1 calorie is the heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay. And 1 calorie is 4.184 joules. Okay. So we'll use this conversion all the time. All right, so now the specific heat denoted by C is the amount of heat needed to raise the temperature 1 kg of object by 1 degree Celsius. Okay, so the amount of heat needed to raise the temperature by 1 degree Celsius for 1 kg of material. Okay, and then the specific heat is a characteristic of the substance. All right, so for instance, if the specific heat is high, you need a lot of heat to raise the temperature 1 gram of one or 1 kg of the substance by 1 degree Celsius. And it turns out that water has a very high specific heat. So you can see here is in water has a specific heat of 4,200 joules per kg per Kelvin. Silicon, okay, so dirt is silicon dioxide, a lot of it is silicon dioxide. So dirt outside has a specific heat of about 700. Okay, so you see the specific heat of water is 6 times greater. What that means is, so let's say, again, now I'm going to rearrange this formula. Okay, Q is M C M delta T. Okay, so what we're going to do is shine the same amount of heat on both land and water. Okay, the specific heat of water is on the same amount of, so the mass is the same, the heat is the same. The specific heat of water is 6 times greater, so its temperature will rise 6 times, 6 times less. Okay, so you put the same amount of heat and the temperature of water doesn't rise as much because its specific heat is much higher, and the temperature of land will rise quite a bit higher. Okay, so the air over land warms up, and the warm air expands, it gets lighter, and it rises up. And what it does is it leaves behind a low pressure, and and here the pressure is higher because well, this air did not rise up, so this pressure is higher, and you'll have a wind blowing from a high pressure to low pressure. Okay, so hello. Yes, I'm recording a lecture, but I'll call you back. Okay. Okay, bye. So you'll have a pressure difference, and you'll have a wind blowing in this direction. At night, the reverse happens. Water holds its heat much, it has a lot of heat, and so it holds its heat, land cools faster, and so now air is warmer over here. This rises, it leaves a low pressure behind, and you get a breeze in this direction. Okay, so it's this difference in specific heats that cause the winds. Okay, and so this is important. All right, so remember, the specific heat of water is very high compared to that of land. Okay, here's another important feature. Okay, the density denoted by rho is the mass per unit volume of a substance. Okay, and again, so if you take take a substance, and if you heat it, now normally all materials, when you raise the temperature, the volume increases, they expand, and when the volume increases, the density will decrease. Okay, when this increases, the density will decrease. So for most substances, when you raise the temperature, the volume increases and the density will decrease. But water is unusual. Okay, so here's the density of water, and you see when the temperature rises from 0 to 4 degrees, when the temperature rises, density decreases for most materials, but for water, the density has increased in this window. So in this small window, water is behaving unusually. And see, the density change is very small, but nevertheless, the density is increased. Okay? And this is important. In fact, what this leads to is, if you try and freeze a lake, it turns out that, okay, so, all right, let's quickly do this. When you freeze a lake, so let's say the outside air temperature is minus 20 degrees Celsius and heat starts flowing out, okay? And when this layer gets to be 4 degrees Celsius, since it's densest, it'll sink, and the bottom layer gets to be 4 degrees Celsius. And once the entire lake gets to be 4 degrees Celsius, now when this gets colder, this top layer gets colder, let's say it gets to 2 degrees Celsius, now this won't sink because it's less dense, and it'll stay up, and now it keeps losing heat, and eventually this will freeze. And ice is ice is less dense than water. Ice doesn't sink, and so now the ice layer will stop heat from flowing out. Okay, so when a lake freezes, only the top surface freezes, and the bottom surface will remain at -4 degrees Celsius. And this is important for biology because then life can survive the winter. Fish can live in this water and survive the winter. Okay, so again, the important thing is because of this little graph, the little bump, and the fact that ice is less dense than water, when a lake freezes, only the top layer freezes. Okay. Now we'll come to a very important concept of latent heat. Okay. Right. So let's say you take a bunch of ice, and that's at -5 degrees Celsius, and you heat it. Okay. So here's what will happen. The temperature with heat added, or the time. So when you heat it, okay, the temperature of ice will rise to from -5 degrees Celsius to 0 degrees Celsius. And then once it gets to 0 degrees Celsius, even though you're adding heat, the temperature doesn't rise and the temperature will remain constant, and all the heat is going into melting the ice. Okay. So the heat is going into melting the ice. And so, well, what is happening to all the energy since the temperature is not rising? What is happening is it's going into breaking the bonds, and it's not raising the temperature. And that is called latent heat. And once all the ice melts, now you can raise the temperature of water. Okay. So when water is going from the solid to liquid phase, when it's melting, all the heat is going into breaking the bonds, and none of the heat is going into speeding up the molecules, and that is called latent heat. And same thing happens when you heat the water all the way to 100 degrees Celsius. So you so this is melting when ice is melting, and then you can heat the water all the way to 100 degrees Celsius, and now the temperature of water doesn't rise above that. So as you're adding heat, the water is turning into steam, and once all of the water turns into steam, then you can raise the temperature of steam. So when phase change happens, meaning when solid to liquid or liquid to gas phase change happens, okay, the heat goes into changing the phase but not raising the temperature, and that's called latent heat. Okay, so this formula tells you how much heat you've added. If you turn that much mass into a new phase from solid to liquid, and that's the latent heat, this gives you how much heat you've added. Okay, and here are two very important numbers to remember. So the latent heat of fusion of water, 80 calories per gram. What that means is to melt 1 gram of ice, you need to add 80 calories of heat. And the second more very important number for us is 540 calories per gram for the latent heat of vaporization of water. What that means is to turn 1 gram of water to steam, you need 540 calories of heat. And this number is very important because here's how we cool our bodies. Okay, so we are warm-blooded animals, and when you get warm and you don't want your body temperature to rise, so when you go for a run, for instance, what you do is you sweat, and then what you're hoping is your sweat evaporates. Okay, and every time your sweat evaporates, every time 1 gram of your sweat evaporates, it takes away 540 calories of heat from your body. And this is one of the best mechanisms for cooling. Okay, so this is we use that latent heat of vaporization of water to cool our body. Okay, every time 1 gram of sweat evaporates, it's taking away 540 calories of heat. Okay, of course, if the humidity is 100%, okay, then your sweat won't evaporate, and then you won't be able to cool down. Okay, so it's very, of course, it's uh, it's dangerous to go for a run when humidity is high, or you don't want to go for a run when your humidity is high, and because your sweat won't evaporate and won't cool you down. So one of the tricks, one of the things in situations like this, the medical industry uses, then what you do is, and we'll see a problem, you give an alcohol rub. The atmosphere doesn't have alcohol, and alcohol will evaporate and cool you down. Okay, except that the latent heat of vaporization of alcohol is about 205 calories per gram. Well, it's not taking off as much heat, but the advantage is the atmosphere never has alcohol, and this alcohol will evaporate fast. Okay, so this is one fast way to cool you down. Okay, so this latent heat is a very important idea. Okay, so here's another thing. The heat of vaporization of water is quite large, which is 540 calorie per gram. It is the energy source for hurricanes and steam burns. So what that means is, if there's steam at if you have if steam at 100 degrees hits you, okay, the steam will condense to water and it'll burn you with 501. Every gram of steel will burn you with 540 calories, and then it's become water at 100 degrees Celsius, and that'll burn you too. Okay, so it has this extra energy per gram. Okay, so that's why steam burns are very dangerous. Okay. So here are the latent heats of various materials. Here's latent heat of water, and this is the latent heat of fusion, meaning melting of water, and this is given in joules per kg. Latent heat of vaporization given in joules per kg, and again this is in joules per kg, and this is equal to 540 calories per gram in these units. Okay, this number is easier to remember. All right, let's look at the process of evaporation. Okay, so you saw that, let me reset this. This is a better one just because the molecules are lighter and they're moving faster. All right, so you can see that this is gas, but if you took a glass of water, the molecules in the water would also have velocities like that. They would have different speeds and so on. And you see, if you have a glass of water, the faster molecules are able to escape the glass, and they're evaporating from the glass. So even at room temperature, if the faster molecules will escape. Okay, so let's take a glass of water, and the faster molecules will escape. Okay, and now if there's moisture in there, there's water molecules coming in as well. When the humidity is 100%, the number of molecules escaping is equal to the number of molecules coming in. So there's no net evaporation. But if the humidity is less than 100%, let's say 50%, there are more molecules escaping than coming in. So at any temperature with less than 100% humidity, you have net evaporation. And since the faster molecules are evaporating, that's cooling down the water. Okay, so, and this is true for all substances. So water and other substances can evaporate at temperatures far below their boiling points. A glass of water will slowly evaporate away in few days. Okay, and this is not just for water, even solids. So even a block of ice, water molecules can escape directly into the air, and this process is called sublimation. Okay, and as long as the vapor, so that's called sublimation. Okay, so ice cubes left in a freezer slowly disappear as water goes from its solid state directly to its gaseous state. So what makes evaporation and sublimation possible at temperatures below the boiling point is the random molecular motion. Okay. There are always molecules with kinetic energies far above the average. Those with large enough energies overcome the attractive force that hold them in a solid or liquid and escape. Okay, so there are enough fast molecules that escape the attractive force of the surrounding molecules. Okay, so so when the humidity is 100%, the number of molecules escaping is equal to the number coming back. And if the humidity is less, then there are more molecules escaping than coming back. Okay, so I've been saying 100% humidity, but that's relative. Anyway, that's relative humidity, and this is what it means. Okay, so at these temperatures, what this table gives you is the saturation density of water vapor in air. What this tells you at these temperatures, the atmosphere can hold, this is the maximum amount of water vapor the atmosphere can hold. So at 20 degrees Celsius, the amount of, for every meter cube of air, the atmosphere can hold 17.3 grams of water vapor. Okay, so when 17.3 grams of water vapor are there for every meter cube, this corresponds to 100% humidity. And so if there's half as much, 8.65 grams per meter cube, that means the humidity is 50%. Okay, and there's more room for water to get in the atmosphere. Okay, and so 50% humidity means this much water vapor at 20 degrees Celsius. Okay, so if you leave a glass of water in the room, then this water will evaporate, because at 50% humidity, the atmosphere has room for more water vapor. Okay. And as you can see, at higher temperatures, the atmosphere can hold more and more water. At 40 degrees Celsius, it can hold 51 grams of water 51 grams of water vapor per meter cube. So a relative humidity of 100% means the air is totally saturated and can hold no more water vapor. So if the humidity is 100%, and if you work out and sweat, this is not going to help you cool down, because now your sweat cannot evaporate and take away the heat. Okay, and so that's why we care about that. Okay, so now, and of course, if the humidity is low, then your sweat evaporates easily. Okay, and and you can cool down fast enough. Okay, so here's one example of use of low humidity. Is found in self-defrosting freezers when air inside is kept very dry to speed up sublimation and prevent frost. Okay. Okay, so you can also dehydrate food doing that. Uh, so the humidity is low, then the food will dehydrate as well. Okay. People find that they're most comfortable when the air has a relative humidity of 40 to 50%. Okay. Lower humidity dries out skin and mucous membranes and cause sinus trouble and other respiratory problems. Higher humidity suppresses the net evaporation rate of perspiration and may cause you to feel uncomfortably warm even at moderate temperatures. Okay, so low humidity dries you out, and high humidity prevents your sweat from evaporating. Okay, so this is the humidity we find most comfortable. Okay, so here's that alcohol rub example. Okay, so we use this in the medical field again. Let's say this person is very warm, and let's say the humidity is high. So sweating doesn't cool them down fast enough. Okay, so what you can do is the following. So one method of reducing a dangerously high body temperature very quickly is to give the patient an alcohol rub. Okay, so if you give the patient an alcohol rub, Now the atmosphere doesn't have any alcohol, so the alcohol will evaporate fast. And every time 1 gram of, so the heat of vaporization for alcohol is 204 calories per gram. Every time 1 gram of alcohol evaporates, it takes away 204 calories. So the relative humidity for alcohol is 0% in the atmosphere. So this alcohol will evaporate fast, and it'll take away 204 calories for every 204 calories per gram. Okay, so in this problem you can see that a 70 kg person is roughly 160 pound person. You can reduce their temperature by 1.5 degrees Celsius or 3 degree Fahrenheit, okay, fairly quickly by giving them an alcohol rub. And what this problem goes through is it shows you that if 430 grams of alcohol, roughly a soda can worth of alcohol, evaporates from their body, they can be cooled down by 3 degree Fahrenheit or 1.5 degrees Celsius. Okay, so again, you'd give an alcohol rub because alcohol evaporates very fast, and if the humidity is high and their sweat is not evaporating. Okay, so that's a way to cool down a person. So a 160 pound person can be cooled down by about 3 degree Fahrenheit by giving them rubbing about a soda can's worth of alcohol on their body. Okay, so we are warm-blooded animals and we maintain a temperature of 37 degrees Celsius. Okay. Now, here's the problem. If body temperature becomes too high or too low, you can cause irreversible damage and even death. So here's what happens. Cell metabolism increases with increasing temperature. So when your temperature rises, your metabolic rate increases, and you're producing increased metabolism generates more body heat. Okay, so your temperature is high to begin with, and then you're producing more heat. And so now if your cooling system can't handle it, then your temperature will keep rising further. So it's a vicious cycle. And if your body temperature rises about 42 degrees Celsius or 180 degree Fahrenheit, your cooling mechanism cannot keep up. So your air conditioning fails. And then, unless there's external intervention, then that can be fatal. Okay, so in situations like this, you can use that alcohol rub that we talked about and cool the person down fast. So similarly, when the body temperature becomes too low, your metabolic rate decreases and you're not producing enough heat to prevent the body temperature from dropping further. So again, if it's too low, it keeps dropping, and if it's too high, the temperature will keep rising. Okay, so if the temperature is too high, it'll keep rising, and if the temperature is too low, it'll keep dropping. Okay. So here the basal metabolic rate of a 130 pound person is 80 joules per second. So a 130 pound person at rest is using 80 joules of energy per second to run their body, and eventually all that heat gets turned into heat, and that you have to maintain your body temperature, you have to get rid of that much heat. If such a person goes on a run, okay, so when you're at rest, your cooling system only has to get rid of that much heat per second. And now if you go for a run, you're producing this much heat. So now suddenly you have to get rid of that much heat per second if you don't want your body temperature to rise. So you see, here's the amazing thing. The cooling system on the drop of a dime has to become 15 times more efficient. Okay, it has to work 15 times harder. So it's like your air conditioner is working 15 times, is getting rid of 15 times more heat. So how do you remove this excess heat? Normally it takes, okay, so So when you go for a run, this is again, normally this is how you get rid of the heat. You sweat and the sweat evaporates, and it's taking away 540 calories of heat per gram. Okay, so this is a very efficient mechanism of cooling. When sweat evaporates, it removes heat from our bodies. In addition to the evaporation of perspiration from skin, there's significant evaporation of water from the lungs. Okay, so this is evaporation from the skin, and when you breathe out, there's moisture in your breath. Okay, and that is also taking away heat. Okay, so so evaporation both from your skin and evaporation in your lungs, or moisture coming out of your lungs, is also taking away heat. Now, when the ambient temperature, when the outside temperature is greater than your body temperature, okay, the only way to cool really is through perspiration. Okay, there's heat coming in because the outside temperature is hotter. You're getting energy via radiation from the outside. All other mechanisms are bringing in heat. The only way you're going to lose heat is via perspiration. Okay, and remember, if the humidity is high, you won't. It's hard to lose heat via evaporation of your sweat. Again, so then the alcohol rub will be one effective way. Okay, so again, perspiration is the only way to lose heat when the outside temperature is greater than your body temperature. So evaporation of sweat is the only method of cooling off that works when the surrounding temperatures are warmer than body temperatures. So heat transfer, now we'll look at heat transfer. So here's a fire, and this solid material can get heat to you. That heat is coming to you with conduction. You can hold your hands there, and what you're getting is heat via radiation. What's happening here is, in the fire warms up air around it, which expands, gets lighter, and rises up. So this warm air rising up is bringing warmth to you. Okay, this is conductive heat transfer, this is radiative heat transfer, and this is convective heat transfer. The convective heat transfer involves the motion of a fluid, okay, in this case, hot air. So the three ways of heat transfer are conduction, convection, and radiation. Okay, in solids and liquids, to a fair extent on gases as well, but in solids, conduction is the main mode of heat transfer. When this end is hotter, these guys have more energy than these atoms. These guys bump into their neighbors and transfer some of their energy there. These bump into them, this transfer some of their energy, and so on. Okay? And eventually, energy is transferred there. Okay, till the entire thing comes to the same temperature. So the rate of heat flow or power is given by the thermal conductivity of the material. Okay, how good a conductor it is. A, the area of cross section. Okay, and the temperature difference between the hot and the cold side divided by the distance. Okay, so this formula gives you the rate at which heat is conducted. Convective heat transfer is, so for instance, here's how a space heater warms the room. Here's the heater. When it's on, it warms the air around it. Warm air gets lighter or expands, and it rises up, okay, by the buoyant force, and that gets replaced by cold air. Okay, so eventually this warm air, okay, and then eventually all the air in the room is warm. The warmest air, of course, is at the top there. Okay. Now, an example of forced convection. So convection is heat transfer, involves the movement of fluid. So convection, heat transfer of energy, involves the movement of fluid. So you have to have some fluid carrying the energy, and So that's how convective heat transfer happens. And we use this in the human body. So an example of forced convection is blood circulation, which can transfer heat from one part of the body to another. Blood flow can be increased. So when you're hot, what you do is blood flow is increased to the skin so you can lose heat. Okay. And when you're cold, blood flow is cut off from the exterior and you keep the blood flowing inside so you don't lose much heat. Okay. So this is how the body can control either getting rid of the heat or preventing loss of heat. Blood flow can be increased or decreased to specific areas depending on the need. If a person becomes overheated, blood vessels to the surface dilate, carrying more blood to the surface for dissipation of heat. Okay. So our body's cooling system is quite sophisticated. We all know about wind chill. Okay. So for instance, a minus 5 degrees Celsius with no wind will feel warmer than, let's say, well, minus 5 degrees Celsius with wind, 10 meters per second wind, will feel colder than, let's say, minus 10 degrees Celsius with no wind. Okay. So wind, what wind does is, okay, your body will warm the wind air, and then that warm air goes away, and then gets replaced by cold air, and so you lose heat energy fast, and that's why this feels colder. So the wind chill factor takes account of that. Okay, so here's how you read this. You read this table. So this is a wind chill factor. Okay, so if let's say the outside air temperature is minus 10 degrees Celsius, and the wind is blowing at 10 meters per second. Okay. So if the outside air temperature is minus 10 degrees Celsius and then the wind is blowing at 15 degrees Celsius, it will feel like minus 34 degrees Celsius. Okay, minus 34 degrees Celsius with no wind. Okay, so that's the effect of wind chill. Minus 10 degrees Celsius air blowing at 15 meters per second feels like minus 34 degrees Celsius. Okay, so that's the wind chill factor. Now we'll talk about heat loss via radiation. Okay, so all objects radiate electromagnetic radiation. Okay, and what this formula gives you is the rate of heat loss. P is the power, which is rate at which you're losing heat via radiation. Okay, so E is the emissivity of object, which depends on the surface properties. Sigma is a universal constant. A is the area, surface area, and T is the temperature in Kelvin scale to the power 4. Now, for children, they have a large surface area to body mass ratio, and so they can lose a lot of energy via radiation, okay, in the cold. So you want to make sure that they're dressed warmly. All right, so these two diagrams illustrate that we lose heat via radiation. So, and humans emit mostly in the infrared region. So here's a picture of this person taken visible. This is a picture taken using visible light, and the same situation taken infrared light, showing you the infrared emissions. Okay. Now what this formula says is, if the surrounding temperature is T0, you're getting electromagnetic radiation from the surrounding, and then you're emitting. If the surrounding temperature is higher than yours, then you're getting net radiation. You're gaining radiation. And if the surrounding temperature is lower, then you're losing energy via radiation. And that's what this formula is. Okay. And you saw this in one of the previous slides. So if the surrounding temperature is higher than your body temperature, you see you're gaining 100 watts, 110 watts via radiation. Okay, and we've seen these temperatures. Okay, so 45 degrees is roughly 90 plus 30 to 120 degree Fahrenheit. Okay, so when the temperature is 120 degree Fahrenheit, you're gaining 100 watts, 100 joules of energy via radiation per second. Okay, so that's the net radiative loss or gain. So different materials absorb radiation differently. An ideal absorber, also known as a black body, is an object that absorbs all the energy incident on it. And for that, E is 1. E, the emissivity is 1. Okay. An ideal reflector absorbs none of the energy. So if something is a good reflector, it's not absorbing any of the energy. So for instance, white clothing is a good reflector, and dark clothing are good absorbers. So in the winter, you want to wear dark fabrics so you can gain you can absorb some of the radiation energy falling on you. While in the summer, you want to wear light colored fabrics so that you reflect sunlight. Okay. All right, so our body has an interesting mechanism for handling cold temperatures. Okay. When surrounding temperatures are low, it's necessary to limit the rate of heat loss of the body. The body does not sweat as much in cold weather. Okay, so because here's the double whammy. In cold weather, if you sweat, the humidity is low, all this sweat will easily evaporate and take away heat. Okay, so you don't want to sweat. So the body doesn't sweat as much. You're still losing heat from the lungs because there's evaporation in the lungs. Thick layers of clothing reduce the rate of heat transfer by conduction, convection, and radiation. Okay. Now, if you didn't have enough clothing, if you weren't wearing enough clothing, and your temperature is starting to drop, then what the body does is you do uncontrollable shivering sets in. Okay, when you shiver, shivering is a clever use of opposing muscles to do work against one another. So the net efficiency is very low, meaning you're not really doing any work. So each muscle is working against each other, but you're producing thermal energy. Okay, most skeletal muscles are involved in severe shivering, resulting in little work and a lot of thermal energy generated, which will warm your body. Energy consumption during shivering is about 425 watts, about the same as cycling. So severe shivering is the same as riding your bike. And so you're generating heat to keep yourself warm. You can also rub your hands. Conscious physical activities are also used, such as rubbing hands together. All these physical activities produce thermal energy to keep the body warm. Okay. So again, when you're cold, you don't sweat as much, so you don't lose heat. And then if you're too cold, you shiver and generate heat to warm yourself. Okay, now we'll look at a couple of other things. So you saw that when water freezes, it expands. Okay, so that's important. When water freezes, it expands and its volume will increase by about 9%. Okay. Damage done to foods when frozen are due primarily to cells bursting by the expansion of water turned into ice. So in your cell, there's plenty of water, and when you freeze a cell, the water freezes, it expands, and the cell will burst. Okay, and so of course the cell dies. Okay, so this is why frostbite is dangerous. And some foods tolerate being frozen better than others, but none tolerate repeated freezing and thawing. Anyway, so you damage your cells by freezing, because when water freezes, it expands and it breaks up the cell. Now let's see how Heat is used in a therapeutic manner. Local and general application of heat have long been recognized for a therapeutic value. For example, heat applied to a sore muscle can significantly relieve pain. The mechanism of relief by elevated temperature seems to be twofold: relaxation of muscles and increased blood flow. Okay, so if your muscles are slow, applying heat, what it does is it relaxes the muscles and increases blood flow to the area and relieves the soreness. Okay. Heat transfer by radiation is also feasible. Okay, so if you want to apply heat therapy, you can also use heat lamps and supply heat via radiation. So, for instance, newborn infants are sometimes placed under infrared heaters to replace the heat that they would have received from their mothers. Okay. Within a few hours of birth, an infant's temperature control mechanism works well enough that the heater is no longer needed. Okay, so there's temperature control mechanism that involves redirecting blood flow and all that starts working well. The removal of heat from body can also be of therapeutic value. The method of removing heat is most often conduction, sometimes convection. Okay, so if you wanted to cool somebody down, you remember the alcohol rub. Lower temperatures act as a local anesthetic. Okay, so for instance, children who are teething are fond of sucking on ice cubes to relieve pain. Swelling can also be reduced by the application of ice packs. Okay. All right, guys. So that's it for this chapter, and I wish you the best on the exam, and I hope you enjoyed the chapter.